we keep doing this until we cross 0. And then we observe that we traveled a distance of about 1.1 with some noise distributed according to a normal distribution. And we return the start value. So what we'd be interested in with this probabilistic program is the posterior distribution of the starting position, given the observation that we traveled about a distance of about 1.1. And this probabilistic program is quite challenging to do inference for, because it contains continuous distribution, has an unbounded loop, and even has an unbounded number of samples. So depending on how many steps we take, we have a different number of samples. So what are inference methods for probabilistic programs? They can broadly be put into two classes. The first one are approximate inference methods, which give a rough answer for the posterior. That usually gets better as you take more samples. So examples for those are Monte Carlo methods such as particle filters and Markov chain Monte Carlo, or optimization-based methods such as variational inference. Examples for such probabilistic programming systems would be Stan, Pyro, or Anglican. And there's the second class of inference methods, which are exact, which means they give a symbolic expression for the posterior, which is mathematically exact. And examples for such systems are the PSI solver, Hakaru supports some exact inference method, and the sum product probabilistic language that was mentioned before in Faraz Saad's talk. All these methods have issues, though. So if we look at the random walk example from the start and run two different inference algorithms on it, two different approximate inference algorithms, we can see the result here. So in red, we see Hamiltonian Monte Carlo as implemented in the Pyro probabilistic programming system. And in blue, we see importance samples. And those two results clearly disagree. So at least one of them must be wrong. And in this case, it turns out that the red samples, the HMC samples, are wrong, because that implementation of HMC only supports, does not support an unbounded number of random variables. This is not to pick on any particular probabilistic programming implementation, but just to illustrate that many inference algorithms have certain assumptions, and those are not always made very clear, and it's also not always easy to verify them. And even if you can verify that all the necessary assumptions hold, so even if you know that convergence should hold in theory, in practice it's often hard to know when the samples have converged. So for example, for multimodal models, this is a notoriously difficult problem. On the other hand, if we use exact methods, these often only work for restricted models, for example, disallowing recursion. So I'm not aware of any exact method that would work on the random walk example from the start. So what is our idea? Our idea is a kind of middle ground. So we want to compute rigorous bounds on the posterior. So we want to be able to say the posterior probability of a certain event E is definitely in the interval A to B. So it gives a definite answer, but it's not an exact number, but just an interval. And we want to do this for a universal probabilistic programming language, meaning it can include branching and recursion. We want to allow continuous distributions, and of course, we want conditioning, meaning an observed statement. What's the point of this? Well, as we've seen at the start, this would provide a ground truth for inference problems, and in that way also help to debug approximate inference methods. And how do we achieve this? Well, there's three methods. The basic idea is to use interval traces and interval arithmetic. To make this practical, we also need an interval type system, which allows us to over-approximate recursion and loops. And as an optimization of a common special case, we also use symbolic execution. And I will explain those approaches in more detail now. Before we get into that, though, let me first remind you of the standard semantics of probabilistic programs. Usually that one is defined, at least the operational semantics, in terms of traces, which record the probabilistic choices made. So in this example, we would have the trace 0.2, 0.8. And traces in general are just lists of real numbers. And we have two functions for probabilistic programs, a value function, which for each trace returns the resulting value of the probabilistic program, and the weight function, which for each trace returns the weight or likelihood of the observations encountered during that execution. And then one can define the posterior of an event E in the standard way by integrating this weight function over the set of relevant traces, meaning traces leading to values in the event E that we're interested in. Of course, we cannot compute integrals exactly in most cases. So our approach is to summarize traces using what we call interval traces. So for example, this trace here has the first element between 0.2 and 0.3, and second element between 0.7 and 0.8. So the first trace on the left here would be in the summary on the right. That's the idea. So these interval traces more generally are just lists of intervals, which are denoted by this blackboard I. And similarly, we have to adopt the value and weight functions. So the value is now a function from mapping interval traces to intervals. And the weight function is maps interval traces to non-negative intervals. And for the posterior, we now also obtain an interval from a lower bound to an upper bound, which I will define in a second. And the idea there is not to have to solve an integral, but just to have to sum over some partition of the trace space. And this partition consists of interval traces. So to illustrate how the value and the weight function work, let's look again at our example from the start. And I will show you what happens during the execution of this program. And we'll see the standard semantics on the left and the interval semantics on the right. So let's say we want to execute this program on the trace 0.6, 0.2, and minus 0.8. And on the interval trace, that generalizes this one, basically. So to do this for each sample, we take the value from the trace in both cases. So the start value is 0.6 or this interval. And then we run the program. So while the position is bigger than 0, we take a step, which is again taken from the trace. And then we perform interval arithmetic in order to update the variables. As you can see, position is still positive, so we keep going, take the next interval from the trace. And as you can see, at each point, the standard interpretation, the value of the variables, according to the standard semantics, is included in the interval semantics. So we keep going until the position is not positive anymore. And then, so in this case, we're lucky because our interval is strictly not positive. If this interval here contains 0 in its interior, then we would not know what to do, and I'll address this point later on. But in this case, everything works out. And we jump to the observe statement. And here again, we need interval arithmetic to get an interval for the PDF of the normal distribution. And finally, the return value is just the variable start, which is also an interval for the interval semantics. So this is how we obtain the weight and the value function. And how do we obtain actual lower bounds now? Well, we have to take a set of interval traces that is non-overlapping. And then we can define for all events that are intervals, I, the lower bound by summing over all those interval traces in the set T and multiplying the volume of that interval trace by the lower end of the weight value, the weight interval, and multiplying by 1 if the resulting value is actually contained in the event that we care about, and by 0 otherwise. And by volume of an interval trace, I just mean the product of the widths of all the intervals. And we can do a similar thing for the upper bound. So if we have a set of interval traces that is what we call exhaustive, roughly speaking, it means that it covers every trace, but it has a precise definition. Then we can define the upper bound for an interval event I by, again, summing over all the interval traces, taking the volume and multiplying it by the upper end of the weight interval, and multiplying by 1 if it intersects the event we care about, and by 0 otherwise. We have proved soundness for these bounds, meaning that the true posterior, a normalized posterior, lies between the lower bound and the upper bound. which is, of course, what you want of such a system. But it could still be the case that the lower bound is always 0 and the upper bound is infinity, which would not be very useful. So we also proved the completeness theorem, which is a bit more complicated, but I'll take you through it. So for every event I that is an interval, and for every epsilon bigger than 0, we can find a countable set of interval traces such that the upper bound and the lower bound are within epsilon of the true unnormalized posterior. And we can do this under two assumptions, namely that the primitive functions in the program are basically continuous. The exact condition is a bit more complicated, but that's the gist. And if we assume that each sampled value is used at most once in each if condition, in each observed statement, and in the return value. You may notice this word countable here, which is already much better than the uncountable set of traces that we have. So there's an improvement. But it turns out that for the lower bound, we can also do with a finite set to get an epsilon approximation. For the upper bound, we need an uncountable set in some cases, which is, of course, undesirable because in practice, we can't actually compute with infinitely many traces. And this is where the next idea comes in, the interval type system. And the idea of this one is to over-approximate recursion and conditionals, such as ones that cannot be resolved by the intervals. So for example, in the random walk program we saw before, if the position variable contains 0 in its interior, then it's not clear whether to continue the loop or not. And this is where this over-approximation would come in. What's the idea? Well, our types keep track of the value and of the weight interval. So if we have a typing judgment like this, program is typed with a value of VV prime and weight of WW prime, this would mean that the value of the program for any trace is in the interval VV prime, and the weight for any trace, again, is between W and W prime. And this type system allows an efficient type inference algorithm, which uses interval arithmetic and in particular uses widening to approximate fixed points. And widening is a common technique in abstract interpretation. Finally, we have a third method, which uses symbolic execution. And this one is just used as an optimization for a common special case. And the idea here is that instead of the previous case, so first of all, we consider each program path separately. And now, instead of using an interval for each sample, we just turn the kth sample statement into a symbolic variable, alpha k, and continue the program execution with this one, with those symbolic variables, which means that the resulting value v will also be a symbolic expression containing those alphas. The if conditions, the guards we encounter along our program path will be a set of symbolic inequalities. And finally, the weights psi from the observations will also be symbolic expressions. And in this semantics, we can define the unnormalized posterior by summing over all program paths and integrating over the set of points that satisfy the guards and where the result value is in the set that interests us, and integrating the product of the weights psi and integrating over the alphas. And we can obtain an upper bound and similarly a lower bound, of course, but I'm just going to write down the upper bound by just taking the volume of the set we're integrating over and multiplying by the maxima of all of the weights. And why is this useful? Well, it turns out that our program only contains affine guards, and the result value is also affine in the symbolic variables. Then this volume can just be computed using standard tools that can compute the volume of a polytope. So we use the Vinci tool for that. And if the weights are also affine, then we can use linear optimizations to obtain the maximum for these. And if it's not just affine, contains other functions, we can combine this with interval arithmetic again. So those are the methods that we use. And we also implemented all these methods and evaluated them on a couple of examples. So first of all, let's see what happens on the random walk program from the start. So in green, you can see the bounds that our system computes. And in blue, again, the importance samples, and in red, the HMC samples. And we can clearly see that the importance samples are plausible, whereas the HMC samples must rerun. We've also tried this on other examples that are hard for Markov chain Monte Carlo methods. For instance, Niels funnel, which is a classic example, and many MCMC methods miss the probability mass around 0 here, but our method has no problem with this. And as another example, we considered a binary Gaussian mixture model. And again, most MCMC methods only find one mode there. In this case, it was the left one, as you can see in blue, whereas our bounds showed that there must be two modes. We also compared with previous work from the literature. So there was a paper in PLDI 2013 where they computed bounds on the probabilities in certain events for probabilistic programs, but this one didn't allow observations and conditioning. But we still ran our system on the same benchmarks, and we noticed that our method is usually slower, which makes sense because it's more general, but we often obtain better bounds than in the original paper. We also compared with benchmarks from the PSI solver. So in the repository for the PSI solver, there's a lot of benchmarks, and we use them as a consistency check, first of all, to see that our method works. And we also noticed that a few examples, few benchmarks in the PSI repository use originally unbounded loops, but since PSI cannot handle unbounded loops, they cut the loops off at some point. And we can see in those two plots that this can make a difference. So in the plot on the left, we see that the loop was cut off at 10 to make it tractable by PSI, whereas our method does not need the cutoff and can actually compute the proper distribution and give reasonable outputs for the later parts of the loop as well. And similarly, on the right, we again see that the bounded loop in blue gives a different posterior from the unbounded loop in green that our system can handle. What are the limitations? Well, our system struggles if there's lots of branching and if the models are very high dimensional, meaning there's many sample statements. And this is, by the way, also the case for many exact methods. Those also don't usually scale very well with number of dimensions. And what is future work? Well, we want to look into better heuristics for finding a good trace partitioning T. And it would be interesting to think about whether we can refine this method into an approximate inference algorithm. So I thank you very much for your attention, and I'm looking forward to your questions.
Thank you, Fabian, for your great talk. So it's already the end of the session, but you have two quick questions. The first one by Alex. So perhaps you can read it and answer it quickly.
In your experiments, which of the three methods were used to generate the green bars? How do you choose which set of trace intervals to run? Very good question. So in our system, we implemented all three methods, and we try to use the last one, the symbolic one, if it's possible, if everything is linear. If it's not, we fall back to the interval, the normal interval trace semantics. And if we then encounter unresolvable conditions or loops, then we fall back to the interval type system. So we use all three methods in a combination.
Okay, thank you. And there is also a question by Hoad about static analyzing and widening of intervals. So if you can read it and answer it.
Yeah, one issue with interval arithmetic static analysis is that the analysis is restricted by the quality of the widening operator. Is there much more to gain by using more sophisticated widening operators if we bother to implement them? Yeah, interesting question. We did not implement a very sophisticated widening operator. We basically take the interval union a few times, and then if this doesn't help, then we just extend it to infinity. But I didn't look very much into more sophisticated widening operators, so unfortunately I cannot say if that's helpful.
Okay, thank you very much. So it's the end of this session. So we have a 15-20 minutes break now, and we'll start with next talk by Maria Gorinova. Let's thank again all the speakers of the session. Thank you very much.